I mentioned at the end of chapter 29 that we would be returning to Maxwell's equations. And here we are. So I've written them down again. So we have Gauss's law, one for electricity, one for magnetism. We have Ampere's law, and we have Faraday's law. So remember, Maxwell's equations were not discovered by Maxwell, but he did understand their implications together. So far this semester we have learned that when we have steady fields, so we have a charge at rest, which gives us an electric field, and we have a charge in motion that then gives a magnetic field. We've also learned that when you vary the magnetic field, you get an electric field, and when you vary the electric field, you get a magnetic field. And these concepts are going to turn out to be important as we go through electromagnetic waves, which we're going to discuss in this particular chapter. So what we have here is we have a positive charge at rest. And so you can see the field lines coming off of the charge. Now I can make the charge move linear, which is kind of what we've been talking about thus far this semester. Just a charge in motion in the positive x direction. But now we're going to deal with oscillations. So we're going to start dealing with field lines that are looking like this. Now we aren't going to talk about the charge anymore, but we are going to examine the behavior of the wave that is now created by the oscillation of the electric field and the magnetic field. So what happens when you have a time-varying electric field and magnetic field propagating through space together? Well, Hertz decided to find out. If you notice, frequency has the units of Hertz. Well, that's named after a scientist named Hertz. And he first used oscillating charge in an LC circuit. And he detected an electromagnetic wave with another circuit set at the resonance frequency. And he was able to produce a standing wave. And remember, standing waves are when you have the wave and then the reflection comes back and it makes the wave look like it's standing still. And so he noted that adjacent waves, or adjacent nodes, and the adjacent nodes give you 1/2 of the wavelength, because there's half of a wavelength in between nodes when you have a standing wave. So he's able to determine what half the wavelength is, multiply it by 2, and use velocity equals frequency times wavelength, because he knew what the frequency was because it was set at the resonance frequency. And he found that the speed of the wave was equal to the speed of light. So we were able to see here through Hertz that an electric field and a magnetic field that vary with time propagating through space together is actually light, because the only thing it travels at the speed of light is light. Now we do have to be careful here. Whenever you hear about electromagnetic waves, there is a wide range of wavelengths and frequencies they could be at and energies, but the speed is always going to be constant. So whenever you hear about different types of waves, such as radio waves, X-rays, gamma rays, infrared, ultraviolet, and visible, they're all different types of light or electromagnetic radiation, or electromagnetic waves, depending upon whatever vocabulary word you want to use. But they're just words used to talk about specific wavelength ranges. So longer wavelengths, very long wavelengths are radio, versus talking about something like ultraviolet, which is just a little bit shorter than blue light. So they're just different words to represent different wavelength ranges, because often the wavelength or frequency of the light has different effects on the world.